Number 12. Number 12 has a reaction of C4H9Cl aqueous plus H2O liquid. That goes to C4H9OH, C4H9OH, and that's aqueous plus HCl aqueous. So I'll just get in the way here to write this, and then I'll move. There we go. Let's move that a bit. Excuse me. Okay, doesn't fit perfectly on the page, but I think we can see everything. In number 12, the concentration of the reactant changes. And this is our reactant right here, because we can see that this is just in water. The concentration of the reactant changes from 0.0562 molar to 0.0431 molar in 85 seconds. What is the average rate of decomposition over this interval? So what is the rate of reaction, the average rate of reaction? Now, this is already balanced, and the stoichiometric coefficients are all 1, 1, 1, and 1. If this one in particular was not 1, we'd have to be careful here. It'd be just not as straightforward. So the rate of the reaction is actually equal to the negative value here of delta concentration C4H9Cl. Okay, and this is what we need to find out. And so the rate is equal to a negative value of, the change in the concentration is, it went from 0.0562 to 0.0431. And so change is always final minus initial. So it's 0.0431 minus the 0.0562. And all of that is moles per liter. So you see that inside the brackets is a negative, and that's why we take the negative. So with this specific example, maybe those of you who didn't quite understand the use of the negative sign, it's a bit clearer now. And that's over a time interval of 85 seconds. So I'll just use my 85 seconds so that my rate units will be moles per liter per second. And that comes out to be, if we just punch that in on the calculator, that comes out to be a positive 1.54 times 10 to the minus 4 moles per liter, capital M, seconds to the minus 1. And if you look on your sheet, that is choice A for number 12. Okay, let's continue actually with number 13. I'll just get a new sheet of paper. Number 13. If a reaction has a rate equation, so that's my rate law equation, that can be written like the following: reaction rate constant times A times B times C. So this is given. Now remember, when there is no number here, it's understood that it is 1. And so I can say that this reaction is first order in A, it's also first order in B, and it's first order in C. But the overall order of the reaction, which is what this question is asking, is the sum of those individual orders. And so if I imagine that the ones were written here, then the overall order of the reaction is 1 plus 1 plus 1. The overall order is 3. So I can write that as third order like that with a little degree sign, and that means the same thing. And so that choice on your sheet is choice C, is the correct answer. All right, let's move along to number 14. on this same video clip. Number 14. This rate law is written in this question as rate is equal to k. First order in A, so that's effectively 1, but it is second order in B, so that one is squared. And it says which will cause the rate to increase the most. The first choice is doubling A. Well, if I double A, then the rate would increase by a factor of 2 to the 1, or just simply factor of 2. In B, it says lowering the temperature. Well, I know that if I lower the temperature, I will definitely lower the rate. C says tripling B. All right, tripling B. So if I change B by a factor of 3, the rate will change by a factor of 3 squared. And that would be a factor of 9. So far that's my biggest effect, really. In D, it says that change would be quadrupling A. Quadruple, that would be 4. So increasing the concentration of A 4 times, the rate would change by a factor of 4 raised to the 1. And so that would still just be 4. And the final choice in E is doubling B. So if I double B, the rate will change by 2 to the factor of 2, and that'll be 4 again, just like in D. And so the biggest change, or the biggest effect by a change, would be C. So which will cause the rate to increase the most? The answer to 14 is C.